Now let me shift the frequency a little bit just to see what it looks like. So to shift that center frequency, in other words off 0, because we haven't done anything off 0 yet, we'll just go over here and say 10. All right. Now, you may go like, what happened? All right, well, I'll tell you what happened. Moment here, it goes up. So first of all, I just shifted the center frequency over by 10, still fixed in frequency. Now, the top picture is interesting. Now I am looking at this. My center frequency is 0, and at 0 frequency, what does that mean? Cosine 0x. No oscillations. Now my center frequency is cosine 10x. Well, cosine 10x, I mean, I have this e to the I 10x multiplying everything. So you see this here? That's like a cosine 10x sitting on that thing. So I have a bump, this hyperbolic secant, times a cosine 10x. So it's a wave packet. Oscillation. So if you want to get rid of it, you could say, well, how about if I just look at the absolute value of that thing? And if you do that, it takes away the phase. And it gives you back that. Okay? All that oscillation was having a group of carrier frequencies sitting around in there. It's frequency components and it has a phase. You just get rid of them. Absolute value stuff like that. That's all I care about. You may care about the phase for more important reasons later, but for right now, that's all we care about. Notice a couple things. If I have a lot of noise on here, I'm going to bury all of this. So, in fact, let's bury all of it and just put in a sea of noise. And you're going to see that basically if I take all this out and this is all noisy, then what do I do? Okay? First thing you got to do, if you have this all buried in noise, is figure out where is this? Where's that center frequency? Second thing you do is once you know where the center frequency is, you can build a filter there and build a filter so you can go back to here. Okay? All right, so let's bury it in noise. And to bury it in noise is amazingly easy to do, right? So you have your function, and there it is. And all you got to do to bury it in noise is for every frequency component you got, let me see where this ends here. So I'm FFTing the signal, right? And all I got to do is add plus noise times rand n. This is 1 by n plus I times rand n 1 by n. That's it. It's like we did before, except I haven't told you what noise is, so let's just do noise is equal to like 20. I just put a bunch of noise on it. Let's look at this thing. Whoa! Tell me if you see anything in there. Okay, now that really becomes a Rochet test, right? Rochard, whatever. The guy, what do you see in there? Keon, do you see anything in there? No? Nothing? Dog? Cat? Your house you grew up in? No? Nothing? Carpet. Nice. Okay, anybody else want to volunteer anything else better than carpet? No? Okay. All right. By the way, this is what you got to work with, right? And here's what my claim is. If I keep taking samples of this thing, in fact, I have this thing. I have 21 samples, right? I haven't made any use of that fact, right? I have 21 samples. This is all white noise. And in there is just this clear line that you cannot see. There is a signal sitting there waiting for you to go get it. Okay? Now let's talk about if you have this, what does this do to here? So that's what it looks like here. What does it look like in the time domain? And not so hard to do. You got to inverse Fourier transform everything. Let's call that UN. All I got to do, I've got to inverse Fourier transform it. So I have to go basically, now if you, shoot, I FFT shifted it all ahead of time, right, and took the absolute value. So let's go and do some of that. Let's take off the absolute value. Let's take off that FFT shift. Okay, all that hard work thrown away. Fine, we'll FFT shift it later. all we have to do is take the absolute value here and FFT shift it there instead. Okay? But U of n now is just the IFFT of uj. Okay? Oh, ut. Sorry. Yeah. So I take row by row, this noisy signal. I inverse Fourier transform it. And now I can say subplot 2, 1, 1. And we can just plot waterfall T, S, absolute value of U, N. Oh, I need my view back. Okay, so here, this is your problem. Tell me if there's anything there. So remember, data analysis is about this. So what I like about these examples is, in your dog problem or in this here, you clearly saw, we already know the answer ahead of time, right? We know there's a signal in there. We know there's this thing going like this through here. You can't see it because I hit it, right? And the objective, if you are the airplane, is to hide yourself. The objective, if you're on that radar, is to, it's hide and go seek, right? But it's whoever's got the better data analysis processing skills, right? There are things here you have to take advantage of. And if you don't take advantage of them, you get no information. Okay? And what's the information you can take advantage of? So first of all, in this problem, you may not even know where a filter exists to put. What happens if this airplane bounces off your omega naught? Suppose, okay, let's play a what-if game. Suppose you develop really great stealth technology. This plane here, you know how to put a nice coating around your airplane, design it so that you send omega naught out, nothing comes back. Now, if you're these guys, you're like, wow, that plane's invisible to me. However, what if you're emitting some other frequency? There's something else coming off your plane, off the engine. It wasn't something I shot out there, but I have this big spectrum of stuff that I'm reading in. And maybe you're emitting at some other frequency some information that I could get. I don't even know what frequency I should be looking for. But if I keep taking measurements, what this is going to allow me to do is come back to this idea here, is to say, here's what I'm picking up, which just looks like nothing. And what I want to start doing is, slice by slice, as I just keep taking information in, start averaging it, because anything that's real signal is not going to cancel out. Noise should cancel out, right? So then, if I get all the noise cancellation happening, okay, sorry for the pause. All right, ready? So if I get all the noise canceling out, I will start to see emerging out of this frequency component a signature there, somewhere. And maybe I don't know where it is ahead of time. And if I see it, then you can say, well, wait, let me put a filter around here. Get rid of everything else. Put the filter there. See what it says over here. See if there's a signal there. Right? So this is the kind of stuff you would want to do. It's all about who's better at signal processing, actually, at the end of the day. All right? So I've given you this example here, which is sort of just using very basic time frequency, which is I can represent the whole signal in time, or I can represent it in frequency. Now, what we're going to move on to is much more sophisticated thinking, which is to say, well, wait a minute, somehow, when I go from time to frequency, if I'm in the frequency domain, it tells me nothing about the time domain. If I'm the time domain, it tells me nothing about frequency. I want both pieces of information at the same time. And this is where time frequency analysis comes in, which is you say, I will trade a little bit of what I know in the time domain for a little information in the frequency domain. I'm not going to give up everything I know in the time domain. They're not separate objects. I'm going to use both at the same time. Okay? Remember, you cannot know everything about time and frequency at the same time. Impossible through the idea of the Fourier transform, the idea of Heisenberg uncertainty. That's not a possibility for you. However, you can sacrifice one for the other to try to get yourself in a situation where you can know a little bit about both and maybe make some information there. Okay? All right, so Wednesday we're going to talk about windowed Fourier transforms, which is this idea of how do I represent both. In the meantime, you have your dog problem, and we'll just keep moving forward from there.